Here we're going to look at some totally inelastic collisions. The first one is with two carts of equal mass. They're going to stick together via velcro when they collide. So we can watch, the video. They stick together and move off together. Um, as as we get this, the data is synced up between the graph and the video. So if I play this, we can see that I give it a push and then they stick together. We can watch that one more time. And then they move off together. Now, of course, this is not a perfectly frictionless scenario, as you can see by the fact that after the collision, there is a negative slope in the velocity time graph. So it's clearly slowing down. You can even see it with the green cart when it's being moving after I give it its initial push. But what we do see is that the velocity of the green cart just before the collision is about 0.5 meters per second. And once they collide, the velocity of the combined mass is about 0.25, give or take, within a hundredth of a meter per second. And that's kind of what we would expect, right? The momentum needs to be conserved. And since we basically double the mass that's moving, we cut the velocity in half. So that's pretty logical there. In this scenario, I've added some masses to the yellow cart. So it's considerably more massive than the green cart, which is going to be hitting it. So you can watch, right? Things slow down pretty dramatically. And if we watch the synced up video, you see that the green cart had a very large velocity, well, a larger velocity, about 0.6 meters per second. And the combination of the two of them together had about 0.15. Because the total mass is much bigger than double, we get a much bigger than, or much more dramatic than half factor by which the velocity changes. Again, as we saw before, there is friction in this system, so it slows down after the collision as they're moving. In the final scenario here for totally inelastic collisions with the velcro, we have a heavier mass. And you'll notice I've moved the masses from the yellow cart onto the green cart, so it's the more massive one hitting the light cart. We can watch what happens. It doesn't slow down nearly as much in this case from the initial condition. And so we can watch the synced up video. Right, you'll notice that the initial velocity here, about 0.5 meters per second, only drops down to about 0.38. So most of the velocity, most of the momentum was in that initial cart, and the combined mass, which is a little bit bigger, but not nearly as big of a difference. It doesn't slow it down nearly as much.